Hello everybody, how are you doing? I hope you are doing well. Welcome to this video. This is the video part number 8 from the test driven development video series, and if you didn't watch the video part number 7, you should watch it at first and then watch this video. Okay, what's on the agenda in this video? Same as the last video, today we are going to complete the Soundex class implementation through test driven development. But before that, don't forget to check out the session 8 branch. Okay, open up the Visual Studio Code and on a status bar. Okay, let me tell you something new. If you don't know that much about Git repository and Git version control system, every session you should synchronize your repository or pull the new changes from the remote repository. Okay. In order to do that, click on branch icon button in the left side of Visual Studio Code. I mean at this point, click on source control icon button and click on this button, and then it shows you a menu, and then on push menu icon, click on pull. Okay, you are done. And then on a status bar, click on branch button and then click on session 8. Okay, let's implement the new test case. Open up Soundex test case file. Okay, for our next test case, we want to tackle the Soundex rule number 3, which two adjacent letters encode the same digit. Also, the rules says that it applies to the first letter. But let's deal with the first part. I mean this part, two adjacent letters encode the same digit at first, and then worry about the second part next. Okay, let's implement a new test case. Test F macro, Soundex encoding. Should combines, duplicate, encodings. Okay, we need an assertion. We can copy the previous one. We should give a new input. I'm gonna give A, B, F, C, G, D, T, and it should return A, 1, 2, 3. Okay, it's a little confusing. Do you agree? Because to understand why A, B, F, C, G, D, T to encodes to A, 1, 2, 3, we have to know that B and F letter both encode to 1, and C and G letters both encode to 2, and D and T letters both encode to 3, and it makes it a little confusing. We can learn these facts from reading other tests. For example, we can learn this from this test case, replaces multiple consonants with digits. We could add some assertions to this test case to show, for example, B and F letters have the same encoding, or C and G letters have the same encoding. But it's not a good idea. We should make this test case more readable and more direct. Okay, how can we do that? We can add some precondition assertions to make it more readable. Okay, let's do it. We need an assertion, and we should call that function that returns the encoding. What was that? Open up the Soundex implementation. Okay, we need encoded digit function. We should call encoded digit function, and we should take it a letter B, for example, it should be same as the return of F encoding. Okay, this new assertion makes this test case more readable and more direct, because it shows B and F letters have the same encoding. Okay, we can do the same for C and G letters, and also D and T letters. Okay, let's run test cases to make sure it's failed. The assertion doesn't compile because encoded digit function is private. Let's fix it. We can turn it to a public function. Okay, let's move this function to the public section. Now it can be compiled. Okay, it's compiled and new test case is failed. How do you feel right now? I really know how you feel. Do you think making private functions public is a bad choice? Or do you want to suggest other solutions to make it more readable? Absolutely, we do have other solutions. Let me tell you. We could make test code, Soundex encoding fixture class is a friend of the Soundex class to see encoded digit function, but a friend is usually a poor choice. We could also move the function, encoded digit function, to another class, possibly named Soundex digit encoder. But this solution also seems over-designed. We could also forget the preconditions, these preconditions or these assertions, and find another way to make our test easier to read. Okay, I don't want to choose another solution. I think making encoded digit public is a good one. But maybe you don't agree because you have always been taught a rule to not expose private implementation details. And maybe you should, and maybe you ask me, shouldn't you follow that rule? Let me tell you the answer. First, we don't expose everything, we just expose things we need. Second, we are not exposing implementation details so as much as broadening the public interface of the Soundex class. We are just adding to it a function that maybe clients of Soundex shouldn't need, but our test case also is a client needs it. And I should mention that use this technique sparingly. Making private functions publicly because of your test client. Often introducing a meaningfully named constant or local variable can be a simpler and more effective solution. Okay, the next step. Let's make this test case pass. How can we pass this test case? At this point, this function, encoded digits, we could introduce a local variable that would track the last digit appended, and we should updating it each iteration of the loop. But it's not that much clean. It's a little dirty. Let's start with the declaration of intent. We can implement a new function which is called last digit. Last digit. It should take a string as input. encoding is empty, it should return an empty string, and else it should return the last part of the encoding word. Okay, I've used this std string constructor that takes a size as first argument and a char as second argument. It creates a string which has one letter size, and it would be this letter, the last part of the encoding word. Okay, and we could call this function at this point. If last digit encoding is not equal to encoded letter, it can append the new encoding to the letter. Sorry, I misspelled this word, encoded digit. I could call encoded digit. Alright, let's run test case to make sure it's passed. Okay, we are done. Let's review what I've done. I've implemented a new function, last digit. It returns the last letter of a string, and I call this function at this point, and I give it the encoding word, and it returns the last digit of encoding word. And in this expression, the last digit of encoding is compared with the new encoded digit that we want to concat with encoding. If it's same, it does nothing. If it's not, actually it concat the new encoded digit with encoding. Okay, now it turns to consider a test case where the second letter duplicates the first. But before that, take a look at the test cases. You see, all of the tests so far always use an uppercase letter followed by lowercase letters. You can see in all of the test cases. But the algorithm shouldn't really care. Let's take a brief pause and implement a couple tests that deal with case consideration. Let's see the rules. We don't have any explicit specification for dealing with cases, but it's part of doing TDD well is thinking outside of what we are given. Actually, creating a robust application requires finding answers to critical concerns that aren't explicitly specified in software specification. Okay, Soundex class encodes similar words to the same code to allow for quick and easy comparison. And I think case consideration doesn't matter in how words sound. Okay, to simplify comparing Soundex codes, we need to use the same casing consistently. Okay, let's implement a new test case. Test f macro Soundex encoding. Soundex encoding, first of all, should upper cases first letter. This is the first test case for dealing with cases. Okay, we need an assertion, and I'm gonna give it a new input A, B, C, D, and the result should start with A. This function, I mean, starts with, it's a function from Google Test Framework. Okay, let's run test cases to make sure it's failed. This test case is failed. The next step, get it to pass. Open up the Soundex implementation. We should change the algorithm in encode. Let me find the encode function. Okay, to uppercase the head of the word, which we expect to be only a single letter. Okay, let's implement a new function. I'm gonna name it upper front. Sorry. It should give a string as input. I'm gonna use toUpper function to turn the char to upper one. Okay, what's wrong? Let's Google up about that. std to upper. Sorry, I missed a spell. I should call it like this, to upper, and str.front. Okay, it works. But take a look at this documentation. This point, you see, the documentation says if you want to use it safely, you should convert the input to on-site char, and it should be better done through a static cast. Okay, let's do it. You should call a static cast to convert the char to on-site char. Alright, now we can call this function at this point. Okay, let's run the test case to make sure it's passed. Alright, what's wrong? Okay, the head return a char, and in upper front we can change its input. Can take a char. And we can change the name of the function to upper. Alright, let's run test cases to make sure it's passed. We are done. All of the test cases are passed. Let me tell you something about what I've done. Maybe you ask me, why don't you use CS-style cast at this point? I mean, this kind of cast. Which you saw in C language. Actually, this kind of cast, I mean CS style cast, is not safe. And in C++, three type of cast introduced. Now I'm gonna play part of CPP conference video 2 to explain more about why should we use C++ cast style. I mean static cast or maybe dynamic cast and other kind of cast which is introduced in C++.
I don't like C-style casts unless you have one very obscure use case. And where's the laser pointer going? Is it working? Brilliant. So, the dangers of C-style casts. So, I'm going to lead by example here. So, here's some code. Looks fairly innocent. Now, who thinks this will compile? About half of you. Okay, it will, and you won't even get a warning for it. But if you were to use the variable y, then you'd be into the wonderful land of undefined behavior. So we certainly do not want this. And this is down to the use of a C-style cast. Take this, for example. All I've done is change it to a static cast. Who thinks this will compile? Absolutely nobody. And they're correct. So you've just avoided undefined behavior here simply by using a static cast and being a bit more specific about what you want. So another example. We've got a forward declared struct, t. We've got a const float. Who thinks that will compile? Relatively few of you. Well, sadly, it will. I mean, we don't even have the definition of t at this point, but it will still compile. It will throw away the constness and will be into undefined behavior once again. Nobody wants this, right? So, if we should just use a static cast instead, who thinks this will compile? Nobody, and you're correct. So, once again, we've been saved by using a static cast in this case, instead of using a C-style cast where we could have these silent little errors. And in fact, I've seen this causing bugs in production code. I won't name the company, but it does happen. It's not just contrived. So what's going on? Why does that code compile? Why does it even work? So, quote from the standard. And I've paraphrased slightly so it makes sense out of context. So, the first thing a C-style cast is going to try is a const cast. I mean, we're already into dangerous territory here. We don't generally want this. But if a const cast can't be used in the scenario we've used a C-style cast, we'll get a static cast. It's normally what people want when they're doing a cast, with an asterisk, which I'll explain later. It'll then try a static cast followed by a const cast. So it's going to desperately try to do whatever you ask. It's like trust the programmer. They clearly know what they're doing. We never make mistakes, right? And if that fails, it'll try a reinterpret cast. It keeps getting worse. It doesn't get any better. Okay? And if that fails, it'll try a reinterpret cast followed by a const cast. So it just keeps falling down and down. And I've only ever needed the latter once ever, and it wasn't the nicest bit of code. So generally speaking, we want the static cast. Yeah. So now I'll explain what's going on about asterisks. Well, when you're doing a C-style cast, when it hits the static cast parts, it can do a little more than a static cast. It can do this. And now I'm not going to explain all of that. You can take it as your own reading. It's in the standard. But if you've got a private base class and you want to cast to a point of that type, generally speaking, you can get away with it with a C-style cast. That is the only time you should ever be using these C-style casts. And if you need to do this anyway, you should probably rethink your code in the first place. So that's my presentation. Please stop using C-style casts and use the C++ cast that you meant. Thank you.
Okay, that's all we have time for this video. In the next video, we will try to complete the Soundex algorithm implementation through TDD. I hope you enjoyed it. Thanks for watching us. See you soon.